Hey, so I figured what we're going to do today is just start maybe doing some review of some of the earlier chapters, and we'll see how far we get, and then that'll be it, I think. And we'll get back some papers, then we'll see each other like in a week and a half, I guess, to do a final or something like that. So, um, so we're just gonna kind of go through the chapters to the best of my recollection of what we talked about. So let's just start way back when there, chapter really two. Remember chapter one? There really wasn't too much going on. It basically is just a scientific method, sort of was all we really talked about out of chapter one. Chapter two really started the class, and that was measurements, right? Basically, I think in that chapter mainly. And we talked about the idea of when we do take measurements, the importance of units, and that there's really kind of two types of system. There's sort of the US or English system, and there is the metric system, basically. And remember that no measurement is useful unless there is a unit, because it does give everybody sort of a reference point as to what that value or number means. When we do take a measurement, if you remember, there's always some degree of uncertainty associated with that measurement. So again, if we had something like a ruler, there's really, as we talked about a lot, kind of two things that you want to look at when you are taking a measurement. You want to make sure that you figure out really what the large markings represent and also what the small markings represent when you're looking at any type of measuring device. So in this case, if we look at our large markings, it represents basically 1 centimeter. We count our smaller markings, and remember, again, we always count kind of after the last large marking is where we kind of start counting. So if we count there, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And obviously we can divide, if you're not sure what that represents, you can divide this by 10 and you'll get basically 0.1 centimeters. And again, in this case, that's 1.1, 1.2, 1.3, 1.4, 1.5, and so forth. Remember that when we take a measurement like this, there should always be numbers that everybody agrees upon. So again, everybody agrees upon, if you look at my arrow, it should be 1.4. It's not exactly obviously at 1.4 as we've seen a number of times. So that is really where the estimate and that uncertainty in that measurement comes into play. Here we would need to record a number, maybe I feel like it's halfway there, and centimeters. So this would be our first uncertain number. This is, I'm sorry, I would go that way. That's our first uncertain number. These are our certain numbers. There you go. And again, you could also, as we talked about, figure out the tolerance or uncertainty in the measurement by taking the smallest markings and dividing it by 2, and you get something like plus or minus 0.05 centimeters, which is the tolerance or uncertainty in the measurement. So if you can't figure out again how far you should take the reading to, but you can for sure figure out what the smallest markings represent, then all you have to do is really just divide the smallest markings by 2, and that'll tell you how far you should take the reading. So here we can see we could go to 2 decimal places, and that is exactly where obviously we should take the reading. So make sure obviously that you know how to do that. And the importance of doing that when we take a measurement is when we record all the certain numbers plus the first uncertain number, in this case, that is basically what significant figures are, which we talked about. So we talked about the proper sig figs. When you do that, that does give you, again, the proper sig figs, which in this case would be 3 significant figures. So it's really important to figure out how far you can take the reading, and recording that first uncertain digit again gives you the proper number of significant figures. That last number again does not always have to be a 5. If it's closer, say, to the next marking, it could be like a 9, an 8, it could be something. But the importance is you would have to, obviously in this case, take it out to decimal places. That led us into, after talking about taking measurements, talking about significant figures. And when we talk about significant figures, again, a reminder that there are some rules when we count sig figs. First one is all non-zeros are significant. So any number that is a non-zero is going to be significant. We always start counting left to right when you look at the number, and you start counting when you hit the very first non-zero number. When we have zeros, right, there's a few different types of zeros. There are the leading zeros, and the leading zeros are not significant. So again, you could have like 400 zeros before you hit that first non-zero number, and none of those zeros are going to be significant. We have trap zeros, or captive zeros is sometimes referred to, and those are significant. So again, a leading zero looks something like this. None of those are significant. We wouldn't start counting, obviously, until we hit that number. If you had something like this, 404, that is a non-zero, that is a trap zero, and that is a non-zero. So this guy would be significant in this case. And really, probably the zero that gives everybody, as we've seen, the hardest time is sort of the trailing zeros. And those can be significant or not significant. And really what depends is, as we talked about, is there a decimal point in the numbers? So it would be significant if there is a decimal point written in the number. So again, if you had something like this, 400 and 400, the top guy would actually have only one significant figure, as it is no decimal point written. With that decimal point there, that's going to turn those zeros at the end to be significant, and it would have three significant figures. And remember that the decimal does not need to be near the zeros at the end. So here we wouldn't count these. We would count this guy. We would count this guy. These two at the end would be counted because there is a decimal point here. So this would have four significant figures. So again, the decimal point doesn't have to be necessarily near those zeros at the end, but it does have to be written and put into the number. The other thing we talked about in terms of significant figures is when you have a number written in scientific notation, which is n times 10 to the n, where this is a number between 1 and 10. And this is a positive or negative number, depending on which way you need to move the decimal point to get a number between 1 and 10. When you do have a number that is written in scientific notation, regardless of really what the exponent part is, all the numbers that come before the times 10 part are significant figures. So in this case, this guy would have 3. That is also why sometimes the only way to get the right number of significant figures is to write it in scientific notation. This would be 2 significant figures. You know, if I had 1.000 times 10 to the 3, that would be 4 significant figures. It is the number of significant figures in scientific notation before you convert it to a decimal. So however it's written in scientific notation, that is how many significant figures there are. Any questions on that review there? Now, we also talked about, speaking of scientific notation, again, just a last friendly reminder, make sure you use your exponent button depending on which calculator you got going on there. Actually, it's times 10 to the end, right in that circle. So remember, always exponent button when you're punching it in so that you do get the right answer. We talked about calculations that involve significant figures, and remember that if we multiply or divide, our answer should have the same number of sig figs as the number with the least number of sig figs. So if we took 3.20 times 1.2, this is 3 sig figs. That is 2 sig figs. Our answer should end up with 2 significant figures in this particular case. When we add or subtract, remember it is a different thing that we're sort of looking at when we're adding and subtracting. We're looking at decimal places. And it's still the smallest number of decimal places is what your answer should have. So if you added together 4.1 plus 1.222 plus 3.45, and you put them together, 277.8. Here it has 1 decimal place, 3 decimal places, and 2 decimal places. We would go here to 1 decimal place in this case. We would have to look at the number next to it, and we would round in this case to 8.8. Remember that has 1 decimal place, but it has 2 significant figures, which might be important if you're going to go take that, obviously done before, and maybe do multiplying or dividing with it. So you do want to be careful on that. Remember that if you are doing multiple types of calculations or multiple calculations kind of in a row, using the answer from one step to the next, it's usually a pretty good idea, as we talked about, not to round too much until you get to the very end. Otherwise, you'll get some rounding errors and stuff like that. Speaking of rounding, right, we never want to do any kind of crazy rounding. We always want to make sure we don't change the value number. So I think this was like the number example we looked at back then, 13,333. And if we wanted 2 significant figures, it really should be something like 13,000 or 1.3 times 10 if you want to use scientific notation, 1, 2, 3, 4. It should not be 13, even though it's 2 significant figures. Again, there's a big difference in the meaning of those values. So remember that you want to round to the right sig figs, usually at the end of the calculation, and you don't want to do extreme rounding that you change the meaning of the number. Remember that also that, you are going to keep some sort of guard digits along the way, but you should keep track of really what sig figs you should be having as you go through multiple steps in the calculation. And in most cases, sort of that last sort of calculation you do that will determine sort of where you'll end up with your answer and stuff like that. Questions on that there? All right, so we talked about obviously different units and the metric system and the SI system, which came about, which is really based off of the metric system. And remember, we have some prefixes, like centi, we have kilo, right, 10 to the 3, all these kind of sort of prefixes. And remember that when you do see a prefix such as this, what that means is that there are in one of the prefix units, like 1 kilometer, there are 10 to the 3 of the base units. So that again is the proper way to use that. Also, if you change the base unit, it doesn't really change the conversion. You still got the same way to use it, like so. Remember that these 2 guys are basically what are known as equalities. And from any equality, you can write 2 conversion factors, where you could say, for example, 1 kilometer over 10 to the 3 meters, or 10 to the 3 meters over 1 kilometer. So, if you had something else as well, like 1 pound is 453.6 grams. That also is an equality, right? And from that, you could write 1 pound over 453.6 grams, or 453.6 grams is 1 pound. These, again, are our conversion factors. Now, when we talk about numbers, there are things that are considered exact numbers. And exact numbers are basically definitions, are things that are counted. And when we talk about things that sort of fall under the exact number in terms of definitions, remember that is if you're doing a conversion between the English to English conversions, those are exact numbers. If you're going metric to metric, that also is an exact number. But usually when you cross over from English to metric, those are not usually exact numbers, and you do need to look at the number of significant figures in those conversions. There are a few that I think there was a list there in that chapter, this being one of them here, they want you to know. Obviously, there's 2.54 centimeters is 1 inch is another exact conversion here as well. And what that means is you do have to take into account, again, the significant figures. The other type of number is a measured number, and that is a lot of times that as well, are just something that you take any type of measured from, and those you do have to look at the significant figures. We set this stuff up doing dimensional analysis. Dimensional analysis, right, is where we kind of set it up where units cancel each other. So if we had, 32.5 grams, we want to know how many pounds that was. We use our conversion factors, and remember that although this is not written as a fraction, it's up on top the unit, and we go opposites cancel. So in this case, we would need grams on the bottom. And we set it up here so that we can clearly see the units canceling out. Grams cancel. Anything on top gets multiplied. Anything on the bottom gets divided. So in this particular case here, 32.5 divided by 453.6, gonna get us 0.07164,903 pounds on our calculator. Here, when we sort of analyze what's going on in terms of the significant figures, this is considered an exact number in this school, so we don't look at it. So we would fall back on this guy. And since pretty much when you set up a problem in dimensional analysis, the only thing you're doing is multiplying and dividing, you're always looking at sig figs basically. So because that's really the only math operation you're doing in this particular case. And in that case, we would want to go to 3 sig figs, which would put me here. I would look at that and I would drop it in this case, 0.01716, and I do need pounds in my units there in that particular case. Now, when you're doing dimensional analysis, this is obviously a very short one. You could do multiple steps together, just going opposites and opposites, which is kind of how they want you to do it here. But if you do get an answer, if it's multiple steps each time, again, I would not round to the very end. So I would take it to a couple of digits and continue on with that number. Any questions on that there? We also talked about, I think, temperature conversions. Remember, there are 3 temperature scales. We got our degrees Fahrenheit, our degrees Celsius, and our friend Kelvin. So as we go here, temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. We want the temperature in Celsius, that's the temperature in Fahrenheit minus 32 divided by 1.8. And if we want our Kelvin temperature, that is our temperature in Celsius plus, and they do want you to use the 0.15 here. So 273.15 is our conversion. Also, obviously, if we want Celsius and we have Kelvin, it would be Kelvin minus 273.15. So these are our different temperature scales, and as you experience this semester, and as I mentioned when we were talking about it originally, I'm going to say these are pretty much the ones you use the most and most often. That is the one that you use the most. As we saw pretty much most chemistry sort of formulas need the temperature in Kelvin, so that is definitely a conversion that we use a lot. I think we then finished up maybe talking about density, and density here in this chapter and in all chapters both is D is equal to M over V. Remember that you can rearrange this and solve for any of those things. So V would be M divided by D, and the mass would be volume times the density. Typical units of density are grams per milliliter or grams per cubic centimeter. And also a reminder, 1 milliliter is 1 cubic centimeter equals the same. When you cube basically a length measurement, you essentially will get a volume in this case. These are typical units you find for solids and liquids. We didn't get too much into this, and next semester you probably will, but typically for gases, though, when you do density as grams per liter is typically the units associated with it. But for the most part, these are the two very common sort of units of density. Now, we can obviously get the volume in a few different ways that we talked about. Clearly, you can just take a volume reading, straight up volume reading from something like a graduated cylinder. You could also obviously do the length times the width times the height if you got some type of cube to equal the volume. And if they're each in centimeters, that is how we get to our cubic centimeters. And the last way to get a volume, which is also very common, especially with density, is volume by displacement. And again, volume by displacement, you start with a container that has a liquid like water. You take some type of solid object and you toss it in there. What will happen is it will displace a volume that's equal to its own. So if you take two readings and you take the difference there between the two readings, you could get the volume of the object by taking the final volume minus the initial volume. And that is, again, a very common way. And we did it in those labs as well, like you threw your stopper into some water, took a volume reading before and then a volume reading after. Questions on that there? So I think that's pretty much there, chapter 2, if I'm not mistaken. Then we went off to, I think, chapter 3. So chapter 3 was a really short chapter, if I remember correctly. We talked about, atoms. We talked about molecules, I think, in there. We talked about compounds. And a reminder that atoms are the basic unit of all elements. And they contain, as we talked about, protons, neutrons, and electrons. Molecules is a combination of two or more atoms. Compound is a combination of two or more atoms of different elements. And remember that when we talk about elements, they most of the time are what are referred to as being monoatomic, basically mean they come as ones. But there are some elements that are diatomic molecules. And again, that lists there hydrogen, nitrogen, oxygen, iodine, bromine, chlorine, and fluorine, going up the group there instead of down. Those guys, again, are elements because they only have atoms of the same element, but they also are molecules. So remember that when we talk about molecules and compounds, there is sort of a difference in a sense of those two. As we talked about, molecules are more of a generic sort of term. It could be the same element or different elements, and they would be considered molecules. But here they do have to be for compounds, different elements. So A reminder that all these guys here are elements, and they're also molecules because, again, they do meet the definition of a molecule, which is two or more atoms together. They are not compounds because they are all the same elements for each of them, so they're not compounds. If you had something like water, water is a molecule because it does have two or more atoms. Water is also a compound because it contains atoms of hydrogen and oxygen. Again, water is not an element. So again, that is the distinction between those two things when we talk about it. Now, we talked about also in this chapter the idea of basically physical changes and chemical changes. And remember that in a physical change, basically what you start with and what you end with is fundamentally the same thing, as opposed to a chemical change, what you start with and end with is two fundamentally different things. So again, most common sort of physical changes that we come across the most, like phase changes. So if we take water in the solid phase to water in the liquid phase, that's basically ice to liquid water. They are both water in this case. They just look different, and that is a physical change. And that is why a lot of things like melting points, freezing points, boiling points, those are physical properties and they're basically result in physical changes. That's because you can very simply take your liquid water, throw it back in the freezer, and it will freeze back and you'll get your ice back in the exact same form. It is still fundamentally the same thing. That is different than, say, if we had a little chemical reaction happening, right, where we make some iron and some oxygen here. Balance it by putting a 4 there, maybe. So this is a chemical change. What we start with and what we end with are two fundamental different things. On the left-hand side there, iron and oxygen are separate from each other. They have chemically bonded on the right-hand side. Make a little iron 3 oxide, some rust, and you can do what you want, for example, for rust, and it will never go back to iron and oxygen. You could use any type of physical means, you won't be able to get it back. Or the formation of water, right? Hydrogen, oxygen, make some water. And again, this is a chemical change, as you could do whatever you want to the water. Once again, you could heat it, you could cool it. You will not get the hydrogen gas back or oxygen gas back without doing a chemical change like the electrolysis of water, running an electrical current over it, which again is a chemical change as well. Questions on that there? Now, that led us to, I think I talk of substances, I think, and pure substances. And a pure substance is really anything that is by itself. So if we had water by itself, that is considered a pure substance. You had just iron metal by itself, that is also a pure substance. You took something like some sodium chloride, solid. That is also a pure substance. But when you put those two guys together and you mix two or more pure substances together, you get a mixture, which is the combination of two or more substances. And for example, here that would make some salt water or some sodium chloride solution, but basically salt water. Now, there's two types of mixtures. There is the homogeneous mixture, and there is the heterogeneous mixture. And in a homogeneous mixture, everything is the same throughout. So when you mix them together, for example, this guy here is an example of that. When you mix that together, everything looks the same throughout. Everything dissolves in each other. It just looks like one sort of phase that's happening there. That's different than a heterogeneous mixture. You see different layers or phases. Sometimes people refer to it. And even if you mix all day, you'll never get them to really look the same. You'll always be able to, usually in a lot of cases, see one of the components in the mixture. So, if you had like sand and water, like we did in that experiment, clearly you could take that all day. You'll be able to still see that sand. No matter how much mixing you do, it will never dissolve in the water. So that definitely is a heterogeneous mixture. Remember that regardless of whether it is homogeneous or heterogeneous, you could always get back the original components of those mixtures. They do not change because this is just a physical change. So this is a physical change here. We know it's a physical change because mixtures are physical changes. Because we can separate these out. So as we talked about, we could do a little filtration action, right? And that's a good way to separate out a solid from a liquid. And when you do so, the solid will stay on the filter paper and the liquid obviously would go through. And that's, again, a physical way that you could separate out a solid from a liquid. Works really good for heterogeneous mixtures when you do have that. Obviously, as well, with a homogeneous mixture like, say, salt water, you can use something like distillation, where you heat it up and the water part of that is going to evaporate. And if you keep this sort of tube that connects the two sides really cold, as the steam goes through here, it's going to cool back down and go through condensation, and you'll get your water over here. You continuously heat it, all the water will evaporate. You'll be left with just the salt on one side, and that's a very easy way to separate out like a homogeneous mixture. The way you're able to do that is, as we talked about, you're using and taking advantage of the different physical properties of those two compounds. Sodium chloride, which is an ionic solid, has a super high boiling point. It will never boil. It will just melt. But water, you just need to heat it up to 100 degrees and you can get it to boil. And that's a way to use their physical properties and physical differences to basically separate them out. You did this basically in a not fancy way. You just took an evaporating dish basically and you heated it up. And again, the liquid part would escape. You wouldn't trap the liquid part or the water part. And you'd have left in your evaporating dish at the end just the salt after you heat it. Any questions on that one there? All right, so I think that was chapter 3, I think. Then we, I think, jumped to chapter 10, which was energy, if I am not mistaken. And remember that energy, also, we talked about kind of heat in this chapter. And heat flows from hot to cold. So the warmer substance there gets colder, the colder one gets hotter. And that is a result of common units of energy, which is joules, or kilojoules are very common. Also, calories, lowercase c, and kilocalories, also very common units of energy. In addition, we talked about kind of exothermic reactions and endothermic processes. And a reminder that exothermic means that heat and energy is released, and endothermic heat and energy is absorbed. So a very common way that we can sort of look at energy is through delta H, and that is our change in enthalpy that we talked about. It's sort of the heat of the reaction, either the heat gained or the heat loss as a result of the reaction. You could actually calculate the delta H for a reaction by taking the delta H of the products minus the delta H of the reactants. Remember as well, you do need to take into account the coefficients when you do that calculation in the equation. These are values that you can look up again in a table. And so, for example, if you had just this equation here, 2a plus b goes to 3c, you could go to the delta H table and look up the values of C, B, and A. We'll just do 2 kilojoules, 3 kilojoules, and 4 kilojoules. And if you were going to calculate the delta H for this reaction, it would be our products first. We do need to take the 3, and we would have to times it by the value in the table for C, which is 2 in my example. We would then minus it from our reactants, also multiplying by the coefficient, 2 times 4 kilojoules, plus our B here, which is 3 kilojoules, and that would be 1 times 3 kilojoules. And in my made up example here, I ended up with, I think, 6 minus 8 plus 3 gives me a negative 5 kilojoules. Now, why delta H is kind of important, or what it also tells us a lot of times, is when we look at the delta H value, if it is a negative value, and the number really doesn't matter, but the sign of it is negative, that is an exothermic process, which means overall heat and energy is being released in this case. If you look at the delta H and it is a positive number, that means overall it's going to be an endothermic reaction, and heat and energy is going to be absorbed in this particular case. We also talked about, in relationship to sort of this, we saw some energy diagrams that are associated with both an exothermic and an endothermic reaction. So again, a reminder that if we look at this sort of energy diagram, we'll do actually this way first. And these are our reactants. These are our products. Could also have one that looks maybe something like this. This, I think. And these are reactants, and these are our products. So this is a exothermic diagram, and we know it's exothermic because when we look at the energy of our reactants are higher in energy than our products. So the only way for us to kind of get down in terms of energy from the reactants to the products is overall energy has to be given off in this reaction, and that would be exothermic. This guy on the right is an endothermic diagram. And we know this because when we compare our reactants to our products in terms of energy, our reactants are lower in energy than our products. And the only way for our reactants kind of to get up there in terms of energy is that you got to put energy in overall, and this is going to be an endothermic reaction. Remember, as we also talked about in the last chapter as well, when we kind of touched upon this, in order for a reaction to take place, there has to be a collision of reactant molecules. They do need to collide in the right location. They also need to collide with the right amount of energy, and that right amount of energy is really the activation energy, which is the energy difference from the reactants to really the peak of the energy diagram. That is our E of A, which is our activation energy. And that is the minimum amount of energy needed for a reaction to occur. And over here on our endothermic, this would be our activation energy. Hill. That hill, as we also talked about in the last chapter, plays a really big role in terms of how fast or slow a reaction may take place. If the reactants have a giant hill to climb, there's probably going to be less reactants that have enough energy to get up and over that hill to the other side. The result of that is you would have a slower rate than if you had a much smaller activation energy. It would take probably, there would be more reactants that have enough energy to get up and over to the other side. Activation energy should always be a positive number. As you can see there in the graphs, it's going up, so it should always be a positive number. When we get to the top of these heels, again, a reminder, this is what is referred to as the transition state. And there's usually a complex up there, which is known as the transition state complex, or activated complex. This would be the transition state. What that transition state complex is, as we talked about, is really as it starts up the hill, these guys are starting to break bonds, they're starting to make bonds. So when you get to the very peak of the hill in terms of energy, you have this sort of intermediate that has partially broken bonds and partially made bonds. So it's something that's really, really sort of unstable and very quickly. Usually this sort of complex will drop down kind of to the other side relatively quickly. Now, when we look at this energy diagram, the way we actually figure out our delta H is by comparing the energy of our reactants to the energy of our products, and that is how you calculate the delta H of the reaction. And again, since it is, as we talked about, the delta H of the products minus the delta H of the reactants, when we look on the left-hand side here, our reactants are a larger number in terms of energy than our products would be in terms of energy. So again, here mathematically, you would be taking a smaller number minus a larger number, and that is how delta H becomes negative in this case, is you'll end up with a negative value when you subtract that difference. Now, when you look at your reactants versus your products over here in our endothermic reaction, this case, the products are actually higher in energy than the reactants. And that means that when you do this calculation for an endothermic reaction, you would actually be taking a larger number minus a smaller number, and that's going to yield you a positive number for your delta H. So again, that is why delta H being positive means that it's an endothermic process, and the delta H being negative is an exothermic process. Any questions on that there? Now, a reminder that you can speed up a chemical reaction. And again, very commonly, a way that you do that is you could add a catalyst, and that will speed up a reaction. Remember, though, that a catalyst, again, is not a reactant. It's not a product. It does not get used up in the reaction. What it does, as we talked about, again, is basically find a more efficient alternative pathway for that reaction to take place. The ultimate result of that is what it does in terms of our energy diagram is it's able to, by finding that more efficient pathway, it's able to lower this activation energy. So this would be a catalyst involved. And because it's able to lower the activation energy by finding this more efficient way of doing the reaction. That will allow more reactants to have enough energy to get up and over to the other side. Everybody's going to be able to kind of get up and over. Our greater proportion of molecules will get up and over a lot easier. The result of that is usually you will speed up your reaction when you add a catalyst. Any questions on that there? Then kind of the main energy calculation that we did in this chapter really was the idea of specific heat. And specific heat is really the energy required to raise 1 gram of a substance by 1 degree Celsius. And we had our specific heat equation, which is Q is equal to ms delta T. And again, this is what we use to calculate the energy as something is in the same phase, usually, our transfer of energy that's happening. Q here is our heat, our energy, and that is usually in units of joules or little calories. M here is mass, which is in units of grams. S is the specific heat capacity. And this is the guy that has the 3 units, joules per gram per degree Celsius, are calories per gram per degree Celsius. Remember that they do want you to know the specific heat capacity there of liquid water. And that was our 4.184 joules per gram per degree Celsius, R1 calorie per gram per degree Celsius. Remember that if it is not liquid water or solid water or gas, like it was in the last exam there, the specific heat capacity for water in those cases is more closer to 2. So it does change depending on the phase that you have. By the way, that in terms of energy is our conversion factor between those 2 units of energy. Remember that there are in 1 calorie 4.184 joules. So that is, again, basically the conversion that we use. By the way, again, in 1 kilojoule, there is 1,000 joules. And in 1 kilocalorie, there is 1,000 calories. So those are also some important conversions as you go through here. Remember that the change in temperature here is actually one of the only places in chemistry that we leave the temperature actually in degrees Celsius. And that is because of the specific heat capacities that we use, they're in degrees Celsius. So we actually do leave the temperature here in degrees Celsius, not Kelvin. If you took physics, they would usually convert it to Kelvin, but here in chemistry, we usually leave it in Celsius. Also really important in this equation is the delta T part. You always want to go final temperature minus initial temperature, because as we talked about, the mass should be a positive number, specific heat capacity will be a positive number. So it is only the change in temperature part of this that could be positive or negative. And that's important because when we calculate Q and we hit a negative number, that tells us overall it is an exothermic process that's happening. And if we calculate Q and it's a positive number, that is an endothermic process. Remember, you could do this as simple as we did in lab with some coffee cup calorimeter. And we could use the change in the temperature of the water, and we could relate that to, whatever we might have threw into the water. We might have done a reaction in the water, which a lot of reactants are aqueous. We also might have threw like a solid in there, which is something that we talked about in relation to this, sort of the transfer of energy that happens in this case. Remember that when we're talking about energy and heat, it is transferring from hot to cold, but we also talk about the system and the surroundings. And remember that the system is really anything that you're dealing with. It could be your test tube, your beaker, the surroundings is obviously everything else. So remember that when, say, the system loses energy, that's going to be negative for the system. But when we talk about the surroundings, that would then be a positive absorption for our surroundings in this particular case. And vice versa, if the surroundings was putting energy into the system, it would be negative for our surroundings and positive for our system, endothermic for our system, and exothermic for our surroundings. We saw this when we talked about, and we did the lab like this. If you took like a hot piece of metal that was heated up, say to 90 degrees Celsius, and you drop that thing or tossed it in gently into our water that was at 25 degrees Celsius, when that hot piece of metal goes into here, its temperature is hotter than the water, which means for the metal, it's going to release and be exothermic. It's going to release all that energy to the water. The result of that, the water here, it's going to be endothermic. It's going to basically pick it up. And what we would end up seeing is a rise probably in the temperature of the water in this case. We would also see the metal, for example, lose its temperature, and it would actually end up at the same temperature as the water in this case, as we talked about, because it will come to equilibrium in this case. Remember, in this situation, which is pretty much what you did with the coffee cup calorimeter, we're really following the change in the temperature of water, and that's because we know for water the specific heat capacity, 4.184 joules per gram per degree Celsius. And what that allows you to do is you could kind of use your specific heat equation twice. You could use it for the water, and you could use all the values there and figure out the heat absorbed, in this case, by the water. And what would happen, let's just say we did that and we would end up with a positive value in this case. Just say we'll call it 125 joules or something like that. What that relates though is we could also then look at the specific heat equation for our metal. And remember that the Q of the water will equal negative Q of the metal, which means that if the water in my made up example here absorbed 125 joules of energy, my metal then would actually release the exact same amount of energy, except that it would be negative for my water because it's exothermic going to be given off. That would allow you to have this number. You would have this number, for example, and you would have the change in temperature. And you could solve for something like we did a number of times, like the specific heat capacity of your metal by rearranging this guy. The other important part of this is because that's going to be negative, when you do the change in temperature for our metal, for example, here, our change in temperature for our metal would be 27 degrees, our final, minus our initial, which would be 90. That's going to give you a negative number, and that negative will turn our specific heat capacity into a positive number, which it always should be in that particular case. So that was a very common thing that we did. Again, we just kind of used the temperature change of the water to figure out how much heat was released or not. When you do this at constant pressure, which most of the time you are, Q will equal the delta H of the reaction at constant pressure. So that's, again, a very simple way that you can actually figure out the delta H for a reaction, just with some coffee cups and a little bit of water or two reactants that you put into the coffee cup, and you kind of follow what's going on. Any questions on that there? All right, I think we're going to lay it up.